I think this one relates to the visual aspects you were talking about earlier. Ross has asked, why are darker colors with higher frequencies, for example, indigo or violet, more restful on the eyes, yet colors which alert us, like reds and yellows, have lower frequencies? It feels counterintuitive.
Okay. Good question. I'm not sure I have an answer to that one. So frequencies in terms of, yes, in the electromagnetic spectrum, that's their frequencies, but the frequencies that they exist at have no relation to then how they're transcribed in the brain, into how they're transcribed into spikes. So that's, again, that would be actually a lovely case study in what I've just been talking about, that we can observe for humans that we feel that is some colors more relaxing than others, but we would have no idea mechanistically why that is from the point of view of the neurons in the brain.
Might be a research project for someone in the future. We had quite a few questions coming through about the section on the rats and the maze and what's happening there. So Marcel has asked, you mentioned that you can remove dopamine from a mouse brain during the experiments. How is that done?
Right. So we didn't do so. I was referring to some old work long ago from the late 70s, done by Patricia Goldman-Rakic. She did a whole bunch of work which really established that prefrontal cortex is the seat of these short-term memories. So she had her animals do simple working memory tasks where they had to look at something, a light somewhere on the screen, the light would go off, and then there'd be a delay period, and they have to, after there being another light would go on somewhere, they'd have to look at that previous location to show they remembered where it was. All nice and simple. And in some of the experiments, they would remove dopamine from it. So what they would do is they would inject a drug into that region of the brain that would block all the dopamine receptors. So there's things called agonist drugs. So they are mostly synthetically designed things, or things we discover by accident that we know will basically fill up all the receptors for a given neurotransmitter, in this case dopamine, which means we can be pretty sure that dopamine, when it's still being released by the neurons that fire it, is doing nothing. It's just spilling out and not having any effect, which is also nice because obviously when that drug goes away, you can recover full function. You can show in the animal that it really is that it's lost its memory, because it could do the task, it stops doing the task, it comes back, does the task again when the drug's gone away.
So a book I'm reading at the moment is talking about neurotransmitters in the brain and how one may do one task in one area of the brain, but might not necessarily do the same task in a different area. Does that affect your work with these spikes? And like, for example, when they when you take away the dopamine from the rats, like, would it have a different effect depending on which area of the brain or which function that you're looking at?
Yes, absolutely would. Excellent question. So yes, so dopamine prefrontal cortex is a really excellent example of that. So also dopamine prefrontal cortex, we think there's a good theories about the fact that it acts to sustain this memory. So its effect on the neurons appears to be to help them fire for longer and more of them to fire together to help sustain this memory. So hence, while you take it away, they can't create the sustained sending of spikes. But if you were to do the same in the striatum, the big chunk of brain just underneath the cortex, where there is huge amounts of dopamine, it's the bit where when you lose dopamine from it, you get Parkinson's disease. If you take dopamine away from that chunk, then you get all sorts of problems with learning, rather than problems with short-term memory. And indeed, if you take away enough dopamine from that chunk, then you get Parkinson's-like symptoms. You get the inability to move, which is about as far from memory as you can apparently get. But yeah, so indeed, the actions of an individual transmitter, even though it's the same molecule, are very different depending on where it's released.
I'm glad I've learned something from that book now. Sam has asked, when discussing the accumulation of evidence prior to making a decision, what exactly is the mechanism for this? In other words, how is the information that any given neuron has sent spikes before stored cumulatively?
Yeah, that's a really good question. So we have a lot of theories for this. So one is that it's so obviously these neurons sit in a in a network together, and they're connected quite strongly to each other. So one idea is what's happening is that this group of neurons, this network of neurons, is being driven by input saying there are dots, there are dots, there are dots. And some of those will be saying there are dots moving to the right, some to the left. So once these neurons in this network start spiking, particularly they start spiking strongly, they'll start making the others spike strongly, which in turn will feed back to the original ones again. So there'll be this feedback loop, which will be driving more and more spikes happening. And that accumulation is this feedback loop, which is being driven by this constant input saying there are dots moving to the right. So in that case, so in that case, we can think of experiments where we can play with this. We can block receptors again in the region and see that it goes away. Of course, that helps. But it's quite hard to test some of these theories because they rely on testing lots of individual connections between neurons that we can't record all of, and we certainly can't go in and turn off an individual connection between certain types of neurons. But our best guess is that it's this what we call reverberating activity, this sort of feedback loop that's slowly building up and up and up the activity. And obviously the speed at which the feedback's working depends on how strongly the input's coming in, which is why it goes up faster for the easier ones. So the easier it is, the more dots are moving to the right, the stronger the input saying dots are moving right will be, the faster the activity will go up.
I'm going to say anonymous because it came under a number or just a letter for this question. Could the small reward being food versus non-food items have an effect on the spikes?
Was there any more context for that question?
No, but if you want some, I can move on to another question and ask them to add more context in the chat.
Yeah, are they talking about the? Yeah, if they're talking about the maze or something else, yeah.
Oh, I'm assuming, yes, this was linked to the rats and the chocolate milkshake, I believe it was.
Okay, so the question was whether the
could the small reward being food versus like something else that's not food have an effect on the spikes that you've been looking at?
That's actually, yeah. In terms of the fact we're looking at prefrontal cortex, that's a good question. I'm not sure whether we would decode the type of reward. So certainly we would expect to be able to decode from the spikes the value of the rewards to the animal. So this is something that we didn't get a chance to look at with this data because the recordings are not that long, but in other data sets, people have looked at how the value that an animal places on a reward determines how active its neurons are, essentially. That so particularly if you take you can do this in two ways. Either you can give obviously variable amounts of reward, right? So the bigger the reward, the more valuable it is. So you can see more spikes being sent when it's more valuable. Or you can just see it happening in a long experiment where the animal is getting bored of the reward. So it's only so much chocolate milk or food pellets it can eat before it's getting bored. So the actual value of each reward is getting less and less over time. So you can see the response is getting smaller and smaller and smaller as it gets more and more bored and sated with whatever it is being rewarded with. So yeah, so certainly in lots of parts of the brain, the number of spikes will correspond to the value of the reward, and prefrontal cortex is certainly one of them. We're not sure we can tell the difference between, say, food and milk per se.
Somebody else has asked, how can you reliably identify which neurons are associated with the condition light on or light off in the Y maze? It's quite a complex stimulus if compared to, for example, line orientation in your earlier example.
Yeah, so we're assuming at that point that so prefrontal cortex being right at the front is right at the obviously receives the most deeply processed visual information. So it's the end of what we think of as both the two pathways that come out of the visual system. We have think of a pathway that encodes for the objects, so all their properties, and a pathway that works out where they are in the world. And we think that prefrontal cortex gets both this lots of information and it's right at the end of these pathways. So so from that the photons from the light falling on the retina of the rat should then create some kind of perception of the fact there is a light source at the end of the arm, which will create one pattern of spikes through the visual system that eventually will end up making some kind of pattern of spikes in the prefrontal cortex. And then if that light source is absent, then there'll be a different pattern of spikes because it will be missing that bit of input. And that's what we're looking for. We're looking for the difference in the prefrontal cortex neurons about whether or not they have information about this perception fed forward from the visual system of this light or not.
Marta has asked, was the rat previously trained or not? Assuming that the rat wasn't, then it would explore the new environment and wouldn't be looking for a reward. So if the rat wasn't trained, why would it return to the beginning of the maze to look for such a reward?
That's an excellent question. So yeah, the rats, one of the reasons we love this data set and we've looked at it so deeply is because the rats were not trained before they went in. So it's one of the few times we have ever had of being able to look at the spiking of neurons in a brain, particularly in cortex, before learning has happened. Typically, when experimentalists do these studies, they train the animals first, then they implant the electrodes. They do that because it's such a high risk thing, implanting the electrodes it's really difficult to get reliable recordings of neurons. So you don't want to implant them and then find out your electrodes are terrible, and then because then you have to train the animals. So generally you train lots of them first, and you implant them, and the ones that work, you look at them. But Adrian took the gamble, and his team he was working with took the gamble of implanting right at the start. So we had these spikes. We could see how they changed during learning. It was great. Yes. So typically, if you put a rat in a box, it will go and sniff around, explore, rear up, and look at a lot of things. But you put a rat in what essentially is a tunnel in a dark room, almost pitch black, it will just run down the tunnel. So it relies on the fact that the rats naturally just want to run down narrow passageways. So they don't explore very much. It just runs straight down the passageway and will get to this junction and choose left or right, just instinctively because it's ahead of it. When it gets to the end, because it gets to the end, it's going to break a little beam of light to the end. It's going to hear this noise go off, this is the delivery of the chocolate milk, and it can smell it and it can taste it and lick it and realizes there was something nice at the end. Great. It takes a little while for it to realize there's no other way forward because it's the end of the arm. And then it has to turn around and walk back along this narrow passageway, sniffing and occasionally as it goes, which is why it takes a whole minute to get back, because rats really hate turning around and walking back. They want to kind of run forward. So typically when you do these experiments, what you actually have is this, instead of this sort of Y-shaped thing, you have this maze that goes in a loop. So you have them choose to go left or go right. And no matter what they do, it sends them back to the start again. And that way they can run around and run around and run around. They do that like, take them 8 seconds to go all the way around. But in this, due to a design flaw, actually, they took about a minute to walk backwards, and that's fantastic. They have this whole minute to look at their brains and go, what were they thinking about?
I like that a design flaw, much like a lot of science, something that probably you didn't think was going to help is actually very useful.
Yeah.
Chin Yang has asked, when you say we cannot record spikes in human brains, is it just a technology obstacle, or is it actually impossible forever?
It's an ethical obstacle. Right? I'll give a short answer to that one. There's a long answer. I'll give a short answer. The short answer is obviously implanting any way we record from individual neurons is invasive. So we implant the electrodes deep into animal brains. So either carbon fiber or tungsten electrodes. We either implant them into the first few layers of the cortex. We have long probes that can go right deep into the mouse brain. If instead we want to record neurons using some of our imaging technologies, where we're looking at, for example, neurons that express a protein that fluoresces according to how active the neurons are, well, then that's doubly invasive. We first have to make the neurons express that protein, so we have to inject something which rewrites the DNA or put a dye in them, neither of which is particularly good in humans. And then we have to record that fluorescing activity, which requires either a microscope or sticking a fiber optic into the brain. Okay. So everything's invasive, which means that it requires surgery, it requires risks. So voluntarily recording from a healthy human brain has never even been an option on the table. Because it's ethically, why would you do an operation on someone just to record what their neurons are doing while they're looking at a screen with a picture of a daisy on it or something? So that is an ethical limit. So there's a technology limit in the fact that, yes, we have no way of recording from individual neurons without doing it invasively at the moment. And the hope, one day, I don't know how we're going to get there. One day we'll have the technology to be able to do it. Yeah, and the long answer is that, of course, occasionally we do record spikes from neurons in human brains, but only do that in people with severe disorders, so either epilepsy or Parkinson's. I can get into that again later. But.
And do you think we'd ever reach the point, because with computational neuroscience, a lot of people are just trying to build a network of neurons to resemble what's in the brain. Do you think we'd ever reach a point where you could analyze that instead of actually needing to go into someone's head? Could you replicate it well enough to then measure what's potentially going on?
So, yeah, so we're getting to the point where we have two strands of models. We have models which are models of brains which are enormous, contain millions of neurons. Indeed, people have published models which they've claimed are at the scale of a cat cortex, for example. But where each of the individual neurons is quite a simple model of the neuron. It doesn't have these massive great dendrites or anything, all the sort of stuff that happens inside the neuron. It's just really a device that takes in its inputs, adds them up, and sends a spike if it gets enough inputs. And then we have some models which are much more detailed, so they have really beautifully complicated individual models of each neuron. So they model all the dendrites and what the axon's doing, all the little things that affect when a spike is sent. And the biggest of those is the models of the Human Brain Project building, where you have maybe 30,000, 50,000 of those types of neurons together. So just creating these models points to the fact that we still have this enormous gap between, we can just turn them on and they do stuff, that's fine. But they have no relationship to anything in the world because they're completely disembodied. They don't see stuff, they don't, they're not thinking, they're just spikes being sent between neurons. So what we're really missing, no matter how good the model is, an understanding of how we relate the spikes to what's actually happening in the world. So yeah, and I build these kind of models, so I understand quite how hard it is to make that leap.
So moving on from the rats, although this is on direction, so it probably links. Brian has asked, how does the brain self-organize in this way in the first place, with individual neurons looking for leftward motion, light, colors, diagonal lines, etc.? In other words, how does it even know what's important to observe?
Ooh, that's a deep question. That's a really good question. So, we know. Oh, there's a lot of answers to that question. Okay, so an answer is that obviously a lot of this, it's particularly the visual system. We know a lot of it is through development. Right? So you're not born knowing about edges at a particular angle that neurons are particularly assigned to, and there are lots of neurons which will end up being assigned to being responsive to particular angles and edges and things in the world. And forward from there, we're responding to things that move in the world. So as far as we can tell, when the brain is created, particularly when it first appears in the world, when it's born, it has the wiring sort of capacity set up to be able to do the computations needed to do things like work out motion and vision in vision. But the neurons responding to right or left are not yet actually assigned that way. It takes the development of our visual system in the world to start assigning them, as we try to experience through the retina, the statistics of what we can see in the world. So at the moment, lots of 2D people. Then they would get that kind of view of all these edges and angles and stuff, and they appear in certain parts of the world. And by the process of how the neurons develop, how they start wiring to each other and they start responding to things, these assigned labels appear during development.
Oh, brains are fascinating, aren't they? Yeah. George has asked, how do spikes relate to EEGs, electroencephalograms? I said that right. Yes, recordings. Yep.
Right. So EEGs, for anyone who doesn't know, so EEGs are recorded from the scalp brain. So I think it's normally 26 electrodes, so 13 on one side, 13 on the other, placed across the scalp. And what they're picking up is sort of very large scale changes in the electrical fields around the brain. So our best guess is what they're picking up generally is a lot of, obviously at that scale, we've got 26 electrodes and there's 17 billion neurons. Obviously, these changes are on the scale of billions of neurons changing their activity together. We can see it most clearly when, obviously, when we're in, particularly where we're in forms of sleep or in rest, like when we have our alpha waves in our cortex. So you can see the EEG has this beautiful waveform, and that seems to correspond to when lots of neurons are then become locked together and are sending spikes together and are stopping sending spikes together and alternating that pattern. Then you can see the waveforms in EEG corresponding. But other than when we're asleep and then this restful phase, the link between the sort of waveform shape in EEG and what's happening in the cortex underneath is quite a mystery. And in any case, as I said, it corresponds to the activity of billions of neurons changing together. So it's quite a coarse view of the world. Sorry.
And this question, I'm just going to copy it over because it's a long one. So I'm actually facing the screen.
Okay.
For those of you who don't know, I've got two screens going on. So Florian has asked, just recently I saw an RI talk discussing where the fundaments of the mind might be, sorry. A theory was that a basic region is located in the brainstem. How do you see chances to investigate this area of the brain for studies you were discussing here?
Okay, yeah, so I'm guessing, so at the top of the brainstem, there are the regions that are heavily involved in simply being conscious. So that's where the centers for sleep and remaining out of a coma exist. So there's various regions where you get a stroke into the top of the brainstem and you immediately drop into a never-ending coma. So I'm assuming they're referring to that. So one of the problems, we know very little even in animals about what's happening at the top of the brainstem because it's really hard to record from. Because on top of that part of the brainstem sits the whole of the cerebellum, and above it, bits of the bits of the hindbrain where they say the superior colliculus and things. So even getting to it is a complete nightmare in animals. So in humans, it'll be even harder. So obviously you never see fMRI images that look deep into the brainstem, except very occasionally because it's not an area that is often associated with exciting things happening in cognition. So it is one of the mysterious areas of the brain. So it's a good area to point at and go, maybe that bit does it, because we don't know. But it would be, yes, it would be lovely to know more about it.
I think I remember the talk that Florian was talking about, and I think we were delving into consciousness of what that is, and the brainstem got dragged in, and like you said, yeah, it was all, we can't quite measure it, but it could be involved in it. It's like, and the final question for the evening is from Laura. Do you have any advice for young people interested in neuroscience?
Okay, toughest one for last. Okay.
Yeah.
Okay. Yeah. Okay. So depending what, obviously, neuroscience is a really, really rich field. Okay, you can find almost anything in it that you're interested in. It runs all the way from geneticists looking at how particular genes are expressed in neurons and how they are evolved in how they control what's happening in individual neurons, to how genes are related to various developmental disorders, for example. So then we have people working at the level of the molecular stuff of what the individual receptors are made of and how that's moved around inside the neuron. People looking at just the individual neuron, people looking at the gaps, the synapses between neurons, then up to people looking at spikes of one neuron, then spikes of many neurons, and then up to the levels of sort of the more cognitive neuroscience end. We're looking at fMRI and EEG and MEG to try and record in the human brain. So a good point to start is to figure out what level you're interested in looking at the brain, because you're gonna have to specialize quite early on to one of these areas. And another thing I would suggest that if in many areas, obviously some of those areas are good, there are sort of hardcore biology areas, just particularly all the physiology stuff where we're recording individual synapses of individual neurons, that requires a lot of technical skill, which is for delicate recording of these tiny things. The body of a neuron is less than 1/10 the width of a human hair. So recording from these things is extremely delicate business, and they're fabulously talented experimentalists. So if that's the route you want, then that's great. If you want to go more into kind of the stuff that I've been talking about, where we're talking about recording lots of neurons, understanding what they mean, then there is a high element of sort of computational mathematical stuff involved. So it's kind of, ideally, every new neuroscientist would come with a good, strong biology training and some background in some kind of maths or physics, which is kind of tough given our education system. But that's where the sort of the meeting of minds is most fruitful, I'd say.
I thought that was good advice. Yeah, keep it broad, but find your specialism. So thank you everyone for watching. If you're in the same time zone, good night. If you're not, good day, good evening, good afternoon, whatever. And hope to see you soon. So thank you and goodbye.
Well, bye now.